Welcome back. Our next topic is similarity and Jordan form. We've seen some of this already, although we haven't used these terms. It's really all about change of basis. So let's remind ourselves how that works. You have an n by n matrix with respect to the standard basis, of course. And now you have a new basis v1 through vn. And you get a matrix with respect to that basis. And what is that matrix? Well, we've seen several times already that the way you get that is you take S inverse AS, and I'll call that A prime for the new matrix, where S is the matrix that you get by putting the vectors V1 through Vn into a matrix as columns. Okay. And we've spent quite a bit of time talking about a very important special case of that, which is when V1 through Vn are eigenvectors. That is to say, A has eigenvectors V1 through Vn, which are a basis. That is to say, A Vi is equal to lambda I Vi. So with respect to this new basis, A is diagonal. And so let's write it D, and we get that D is equal to S inverse AS. This is diagonalization of the matrix A. So basically what we're going to be doing now is talking more about change of basis, and especially in cases when you can't necessarily diagonalize. And this is called similarity. So let's define the terms here. Suppose I have a matrix A and any n by n invertible matrix S. Then I say that the operation taking A to S inverse AS is called a similarity transformation. And also, if we have a matrix A and another matrix B, which is S inverse AS, we say that A and B are similar matrices. And the whole point here is that when you have two similar matrices, you should think of them as really being the same linear transformation, just written down in a different basis. And since it's the same linear transformation, it's going to have many properties in common. These two matrices will have properties in common. They'll look a little bit different, but in many essential ways they will be similar. So for example, one thing that's obvious, we've seen this several times before, is if you take A to S inverse AS, first of all, this operation is reversible. You can go back from S inverse AS by multiplying on the left by S to get back to A. And another thing is that the determinant doesn't change. The determinant of A and the determinant of S inverse AS are the same. I mean, we've seen this in the diagonalization process, but it's quite general because the determinant of S inverse AS is the determinant of S inverse times the determinant of A times the determinant of S, and the first and last terms cancel, and you just get the determinant of A. So it's got nothing to do with diagonalization, it's just a property of similarity transformations. And similarly, the trace of A and the trace of S inverse AS are the same. Why is this? Well, there's a basic property that trace of xy is the same as trace of yx. You can change the order. So the trace of S inverse AS, what I'm going to do is write that as x times y, where y is AS. And now switch the order, you get AS, S inverse, and the S and S inverse cancel, and you get the trace of A. Okay, so trace and determinant are preserved under a similarity transformation. And another basic fact is that A and S inverse AS have the same eigenvalues. Why is that? Well, you find the eigenvalues of A by computing the determinant of A minus lambda I. Is that the same as the determinant of S inverse AS minus lambda I? Because those are the polynomials that you need for computing the eigenvalues of these two matrices. Well, S inverse AS minus lambda I, what I'm going to do is I'm going to put an S inverse and S on both sides of this lambda I. They cancel, so that's not really changing anything. And now what I'm going to observe is that you can pull the S inverse out on the left and the S on the right, and now they really cancel. And so you see that these two determinants really are the same, so they have exactly the same eigenvalues. Well, what about the eigenvectors? They have the same eigenvalues. Do they have the same eigenvectors? Well, let's see. Suppose AV is equal to lambda V. And now I have this new matrix S inverse AS. It also has eigenvalue lambda. How do I find an eigenvector for it? Well, it's easy to see it's not just going to be V. That wouldn't make much sense. But I'm trying to find a vector W such that S inverse ASW is equal to lambda W. Well, the whole idea is why not arrange that SW be this vector V, because then I'll have an AV on the left side of this equation. So let's say SW is equal to V, which is W is equal to S inverse V. And then let's check S inverse ASW. Well, that's S inverse AV, which is S inverse lambda V, which is lambda S inverse V. And what is S inverse V? Well, that's W again. So that's lambda W. So indeed, S inverse ASW is equal to lambda W. So the eigenvalues of these two matrices are related by the matrix S. And the precise statement is this: if A has eigenvector V with eigenvalue lambda, then S inverse AS has eigenvector S inverse V with the same eigenvalue. Okay, so here's the basic idea. We have a matrix A, and what we'd like to do is pick a basis, V1 through Vn, so that the matrix with respect to this new basis, which is to say S inverse AS, is as nice as possible. Okay, I can pick any basis I want. I'll get lots of different matrices B. Pick the one which makes this B as simple as possible. That's what we're going to be talking about for a little while now. So the sort of gold standard is if you can diagonalize it. If you can make B diagonal, then how could you get anything better than that? So the only new thing to talk about is what if you can't make it diagonal? All along we've sort of been assuming that all of our matrices are diagonal. Many of them are, but certainly they're not all. So here, for example, consider this 2 by 2 matrix. Is this diagonalizable? Well, before we just apply brute force, let's apply a little thought. Its determinant is 0. Its trace is 0. So if it were diagonalizable, it would have to be to the matrix lambda 1, lambda 2, where the determinant and the trace are both 0. You see that forces both lambda 1 and lambda 2 to be 0, which is to say I would diagonalize it to this matrix, which of course is ridiculous. So this matrix is definitely not diagonalizable. Well, let's look at that a little bit more from the sort of more computational point of view. If I compute the eigenvalues, I see that the only eigenvalue is 0. And what's the null space? Well, it has this vector 1, 1 in it, because A V1 is equal to 0 V1. And what are we going to take for V2? Well, let's take anything. There are no more 0 eigenvectors, so let's take 1, 0, for example. So then I get this for S, and S inverse looks like this. And if you just compute S inverse AS, what you get is, let's see, when you do this calculation, you get 1 minus 1, 0, 0, and then you multiply it like this, and you get 0, 1, 0, 0. So there you go. The eigenvalues are 0 on the diagonal, but it's not diagonalizable. The best that you can do is get a 1 in the upper right hand corner. So this is a very important example. This is kind of the starting point of the theory of the Jordan form. So let's talk about that a little bit. What is Jordan form? Well, the main point is we need to come to terms with these non-diagonalizable matrices. We know how to diagonalize a matrix. What's the best we can do if it's not diagonalizable? And we saw this example 0, 1, 0, 0. A very simple generalization of this is lambda is on the diagonal with a 1 in the upper right hand corner. This is very similar. This is not diagonalizable. Why not? Well, it's essentially the same reason. How do you check if something's diagonalizable? The sum of the dimensions of the eigenspaces have to be the dimension of the space, which is 2. Well, there's only one eigenvalue here, which is lambda, and the dimension of the lambda eigenspace is 1 and not 2. The only vector in it is a basis of the eigenspace is the vector 1, 0, or the eigenspace is x0, which is one-dimensional. Unfortunately, it's not two-dimensional, so this matrix is not diagonalizable. Let's look at a 3 by 3 example. Suppose I took A to be something like this. I took some numbers down the diagonal, alpha, and then 1 on the so-called superdiagonal. Let's compute the eigenvalues of this matrix. Well, you all know when you have an upper triangular matrix, the only eigenvalue is the diagonal entry, which is to say alpha. So there's only one eigenvalue. So is this matrix diagonalizable? Well, you have to compute the dimension of the alpha eigenspace. And of course, it's not 3. Let's check what it is. If you subtract alpha from the diagonal, you get this. What's the dimension of the null space of this? Well, go back a few weeks. You know how to compute that. It's 3 minus the rank, and the rank is 2, and therefore the dimension of the alpha eigenspace is only 1. Okay. So this matrix certainly isn't diagonalizable. Okay, now I want to take a little have a little digression here. This notion of being diagonalizable or not is rather unstable. And I'll illustrate with this with the following example. This matrix is not diagonalizable, but if I perturb this second term by the tiniest amount, this incredibly does become diagonalizable. Let's see, how does that happen? Well, rather than write out these crazy numbers, the main point is if you have a matrix like this where A is not equal to B, then it's diagonalizable. We know that. It has two distinct eigenvalues, A and B. So how does that work? Let's just do a little calculation to see what's going on here. So if the A eigenvector is 1, 0, and if you just do a little calculation, you'll see that the B eigenvector is this vector 1b minus A. All right, so I'll just check. If you apply it to 1, 0, you get A0. And if you apply it to 1b minus A, you get A plus B minus A, and B times B minus A. And that works out to be B times 1b minus A. And there's a slight misprint here. But that is correct. B times 1b minus A. So in particular, if A is 1 and B is this number slightly bigger than 1, this vector V2 is the second coordinate is very close to 0. In other words, this second vector is extremely close to the first eigenvector, which was 1, 0. And that's why you have this instability. If A was equal to B, these two vectors would be coming out to be literally each other, and they're not linearly independent. So it's not diagonalizable, but as soon as you tweak B by the tiniest amount, they become distinct. All right, with that caution in mind, let's talk about the Jordan form. A Jordan block is the following. It's a matrix with a single number down the diagonal and ones on the superdiagonal. The superdiagonal is the diagonal thing just above the diagonal, and zeros everywhere else. And the big theorem, the theorem of Jordan form, says that any n by n matrix can be put into the following form. That is to say, you can find a basis v1 through vn such that with respect to that basis, you do the usual construction S inverse AS. You can get the matrix to be the following. It's got a number of Jordan blocks down the diagonal, J1 through Jn down the diagonal. These are square blocks of various sizes, and each one of them is a Jordan block. And the theorem is that any matrix can be put into that form by the appropriate choice of basis. So let's talk about that a little more. We'll say a Jordan block of size k is a matrix like this, which is k by k. And we allow k is equal to 1, in which case it's just a single 1 by 1 matrix with a lambda. So the diagonalizable case is when all of the Jordan blocks are of size 1. That's the nicest case. And the non-diagonalizable case is when you have Jordan blocks which are of size bigger than 1. For example, this fellow here, it's a single Jordan block of size 2 with lambdas equal to 0. Here's another example. Take this matrix. So this is a matrix which has 4 Jordan blocks of size 2, 1, 3, and 1 respectively. And that's a typical case. You have a bunch of blocks down the diagonal of different sizes. All right, here's the second part of the theorem, which is a uniqueness statement, which is, suppose you have two matrices A and B, and we want to know if they're similar or not. Well, the theorem is that they're similar if and only if they have the same Jordan form. That's an incredibly powerful fact. And when I say they have the same Jordan form, you're allowed to reorder the blocks. You can put them in any order you want, but after we say that they're the same, if they're the same up to reordering. So let's see an example of this. Suppose A is a 3 by 3 matrix and its only eigenvalue is 2. Then we know the only possibilities for A are the following. It could be diagonal, it could have this form, or it could have this form, which is to say a 2 by 1. The second case it's a 2 by 1, and this third case it's a Jordan block of size 3. And the way you tell the difference is, in this case the dimension of the two eigenspaces is 3, whereas in this middle case the dimension of the two eigenspaces is 2, and in this case the dimension of the two eigenspaces is 1. So what you see is that every time you add a 1 to a Jordan block, what the effect that has is it decreases the dimension of the corresponding eigenspace by 1. So the size of the Jordan blocks are intimately tied up with the dimensions of the eigenspaces. So here's an example. Take this matrix. I won't bother doing the computation, but it only has one eigenvalue, which is 2. And so we do this usual computation. You subtract 2 from the diagonal and you get this matrix. And you ask yourself, what is the dimension of the two eigenspace of this? Well, there's a linear relation between these rows. The sum of the first two is the third, so you can do that to eliminate the third. And now clearly the first two are linearly independent. This has rank 2. And presto, you know that the dimension of the null space is 1. And without doing any further computation, the Jordan form must be this. Okay, very good. We'll see you next time.